Okay, hello everyone. My name is Andrey Ignatov, and today we are going to talk about deep learning on smartphones. So the history of deep learning is closely related to hardware that is used for running the corresponding algorithms. And though the first deep learning concepts were released long time ago, the current success story of deep learning began only after the year 2010, when it became possible to accelerate neural networks with general purpose consumer GPUs. And after that, the size of the models also increased. They started to show state-of-the-art results on many data sets. And after the success of AlexNet, basically people started applying them to many other topics. And some topics were, actually many topics were related to mobile devices. For instance, topics like image enhancement, face detection, natural language processing, voice assistants, and so on. So it became clear that there is a clear benefit from running neural networks on smartphones, and for doing this, one basically needs two components. First is software, second is hardware. So we'll start with software. TensorFlow Mobile can be considered as the first mobile deployment library that can be used for practical applications. And it was released in 2015. It was able to run standard TensorFlow models and was supporting almost all TensorFlow operators. All computations were running on CPU, and this was basically its biggest disadvantage. So it was not possible to accelerate models with GPUs or NPUs. Hardware acceleration was addressed in several research topics, but unfortunately they didn't get much better results than in case of TensorFlow Mobile. After the release of TensorFlow Mobile, all SoC vendors presented their own solutions, their own SDKs for accelerating neural networks on their platforms. And with this SDKs, it finally became possible to significantly speed up AI inference on smartphones, on mobile devices. The only problem is that all these SDKs are incompatible with each other, and they can run only on hardware from the corresponding vendor. So if you create an application with Qualcomm SNAPI SDK and running on MediaTek device, it will crash, and vice versa. So if you are going to use SDKs for accelerating inference, you basically need to create 5 different versions of the application. So one default and one for each platform. To address this problem, Google presented Android Neural Networks API in Android 8.1. So the idea here was to create a unified API for accessing AI hardware acceleration resources. And it works as follows. Your mobile machine learning library, instead of running the computations on some hardware, it just delegates, transfers the entire model to Android and NNAPI layer. And this layer checks if there is some registered hardware that can be used for inference. If yes, it passes the model to the corresponding hardware. Otherwise, it runs everything on CPU. And together with Android and NNAPI, Google also introduced TensorFlow Lite framework. It was supporting only a small number of TensorFlow ops. It was at the beginning much slower than TensorFlow Mobile, but it was compatible with NNAPI. So it was possible to accelerate TF-Lite models with TensorFlow Lite framework. Though the entire concept was looking great, so we have a unified API, actually, it had a couple of serious issues. First of all, you should understand that NNAPI is not equal to hardware acceleration. NNAPI is just a middle layer between high-level machine learning libraries and actual device drivers. So if there are no drivers, there won't be any acceleration. And these drivers should be written by SoC vendors. So Google is not creating these drivers. So SoC vendor should write the drivers and send it to a smartphone manufacturer. Then smartphone manufacturer should integrate them into Android firmware and send this updated firmware to the users. So, and as a matter of fact, this is done only for a very limited number of devices. So the majority of devices do not have these drivers, and therefore are running still everything on CPU. Second problem is that NNAPI is supporting a very limited number of ops. So first version only 28 ops, and it was able to accelerate just very simple models. And also it contained a number of critical bugs, so actually it was unusable. The current version 1.2 that comes with Android 10, it contains 94 ops. But, well, this is already better, but still not enough for many custom models, and, for instance, not enough for almost all natural language processing models. Next problem is coverage. So right now, probably around 15% of devices are running Android 9 and above. And only a small percentage of them have the drivers. So if you are developing your application with Android NNAPI, probably you'll be able to get acceleration on 3–4% of devices. And the final problem, the biggest problem are bugs. So each new version of TensorFlow Lite and NNAPI, they are coming with a number of critical bugs. For instance, in version 1.14, when you are running neural networks, during the first 2 inferences, the outputs were random, and even the range was incorrect. So you are expecting to get something between 0 and 255, and suddenly you are receiving 10,000. And this bug was not noticed by TF-Lite team for 2 months. Another issues are related to memory consumption, performance degradation, broken ops. In the latest version, it's no longer possible to accelerate quantized models because Google updated tutorial how to convert them. And when you're using this tutorial, they cannot run with models cannot run with hardware acceleration. And yeah, right now on TensorFlow Lite, on TensorFlow GitHub repositories, there are almost 5,000 issues related to TensorFlow Lite. So if you decide to use TF-Lite, you'll have lots of fun. Yes, and the only way how to avoid this problem is to avoid all issues is to use TensorFlow Lite Delegates. So this functionality was added quite recently, and it allows you to write your own library for running TensorFlow Lite models on some particular hardware. So, and you can tell TensorFlow Lite to use this delegate instead of an NNAPI. And in this case, the entire NNAPI path is avoided. And these delegates can be again written by SoC vendors, and you can integrate these delegates directly into your program. So there is no need to integrate these delegates into Android operating system. They can be, you can use them externally. From developer's perspective, you just need to change one line of code. So instead of adding an NNAPI delegate, you need to add some custom delegate. You're adding some custom delegate. And the advantages are pretty clear. So in this case, you can overcome all NNAPI issues. So in this delegate, one can add many new ops that are not supported by an NNAPI or some extra functionality. Better performance and optimization, simply because you're using the latest version of the drivers that optimize drivers. Delegates are independent, well, can be independent from Android version, so technically every SoC vendor can write delegate for almost any Android version. And yeah, therefore you can add support for legacy devices and cover almost all mobile phones that can be used for accelerating AI inference. So a quick summary. Yeah, and almost all SoC vendors are already writing their delegates, or some of them have already presented something. So it's better to use delegates. So quick summary. TensorFlow Mobile is already deprecated, can run models only on CPU, but can run the majority of TensorFlow models. TensorFlow Lite supports much smaller number of ops, but is compatible with Android and NNAPI. If you're using an NNAPI, use it only on Android 9 and above. And if TensorFlow Lite delegates are available, use them instead of an NNAPI. And also, just a couple of months ago, the first experimental build of PyTorch Mobile was introduced. Unfortunately, it is now mainly focused on CPU inference and therefore not yet very interested in terms of accelerating inference. So, second topic, hardware. As you remember, in 2015, all SoC vendors realized that deployment on smartphones is something unavoidable, and they started to create some special hardware for running deployment models. Because running these models on CPU is completely inefficient both from the point of speed and power consumption. So, for instance, Qualcomm modified their DSP. They presented Hexagon DSP for running quantized models. Huawei released a standalone NPU, and so on. So right now we can distinguish 4 generations of mobile SoCs based on their AI performance. So first generation is a broad one. It consists of all legacy chipsets that never got any drivers for running neural networks. But it is still possible to use many of them with some external SDKs or delegates. But in almost all cases, the inference might be even slower than in case of pure CPU inference. but it is still possible to run neural networks on some non-CPU hardware. Okay, second generation of devices, they were released after 2017. They support Android and NNAPI and show typical AI performance for the year 2018. So for Qualcomm, 3 chipsets, Snapdragon 845, 710, 670. All these chipsets are running quantized models on Hexagon DSP and floating point models on their Adreno GPU. HiSilicon released Kirin 970 with a standalone NPU designed by Cambricon company, and this NPU can run only floating point models. Samsung released 3 chipsets, all are accelerating deep learning networks with their GPUs. MediaTek released Helio P60, P70. They use an APU, AI processing unit, basically another name for NPU, for running quantized models, and GPU models are accelerated on Mali GPU. And floating point models are accelerated on Mali GPU. And Helio P65, everything is running on its GPU. Third generation of SoCs released after 2018 show typical performance for the year 2018. Qualcomm 4 chipsets, same as before, Hexagon DSP is used for quantized inference and Adreno GPU for floating point inference. HiSilicon released Kirin 980. Basically, it has the same NPU, but now with 2 cores. Samsung 2 chipsets, Exynos 9825 and 9820. Right now, everything is running on their Mali GPUs, but these chipsets also have a standalone NPU. Unfortunately, drivers for this NPU are not yet publicly available. And MediaTek released Helio P90 with the second version of their APU that now can run both floating point and quantized models, and Helio G90 with previous generation of APU and Mali GPU for floating point models. And the present generation, the latest, 2 Snapdragon chipsets, again, same as before, Hexagon DSP for quantized models, Adreno GPU for floating point models. HiSilicon released 3 chipsets with new GPU that was designed by HiSilicon and is using their in-house DaVinci design. Samsung 2 chipsets, Exynos 990 and Exynos 980. MediaTek released Dimensity 1000 with the 3rd generation of their AI processing unit. And Unisoc, this company was formerly known as Spreadroom, released Unisoc Tiger T710 that contains a dual-core NPU designed by Imagination Technologies, the same company that is developing PowerVR graphics. So all mobile SoCs listed on the last 3 slides, they have Android drivers for accelerating AI models. All chipsets not listed on the last 3 slides don't have and will never get Android drivers for accelerating models. So very simple. And the last topic, the most interesting, benchmarking. Okay, to check the performance, the actual performance of all these chipsets, we used a benchmark application developed by us in ETH Zurich. This application is using TensorFlow Lite as a backend and is accelerating models using Android Neural Networks API and TensorFlow Lite Delegates. It consists of 11 sections running MobileNet v2, Inception v3, Inception ResNet v1, LSTM, SRCNN, VGG19, SRGAN, UNet, ICNet, DPTRSNet, and memory SRCNN models. And depending on the section, it checks the floating 16, floating 32, in-tape performance, CPU single and multi-thread performance, single throughput inference time, memory performance, initialization time, and accuracy. And also, when the benchmark is running, users can see visualization of network's outputs. And at the end, they can see detailed results for each section, each test, each model. And this application is publicly available, so everyone can download it from Google Play. So here you can see the results for all mobile chipsets that are providing acceleration for floating point models. Also, the results, Snapdragon 835 denoted by magenta, it was running everything on CPU. You can also see the results for several desktop NVIDIA GPUs. In their case, acceleration was achieved using CUDA and cuDNN libraries. And there are also results for several Intel CPUs. Here, acceleration was achieved with Intel MKLDNN library. So the most important message from this slide is that deployment on smartphones is no longer just a buzzword. So the latest generation of mobile SoCs, they are already showing the performance close to NVIDIA GeForce GTX 950 desktop GPU. It's basically a mid-range NVIDIA GPU released just a couple of years ago. And also the performance is almost twice better than the one of the latest Intel 8-core flagship SoC. So this means that you can really run very large, quite complex models on smartphones, and this will be pretty fast. But of course only on the latest generation of mobile SoCs. On old SoCs, acceleration won't be that impressive. If we're comparing just only mobile chipsets, then here the best results are shown by HiSilicon Kirin 990 chipset and MediaTek Dimensity 1000. So they are 2 and 3 times faster than all other chipsets than their competitors. Int 8 inference, quantized inference, here the best results were demonstrated by MediaTek Dimensity 1000 chipset. It was significantly faster than all other mobile SoCs. And one other important note here is that accelerating quantized models with GPUs is not really efficient. So in the majority of cases, performance you won't get any astonishing acceleration. So maybe 2 times, maybe 3 times, but not like 10 times acceleration. And in some cases, the resulting performance might be even slower than in case of pure CPU inference. So you can find the results for all mobile phones, for all mobile chipsets, and for the majority of desktop CPUs and GPUs on our project website, aibenchmark.com. We are updating these results regularly. And today I have covered only a small list of topics, so I did not go into comparing quantized and floating point inference, didn't talk about the accuracy that we observed on mobile devices, and you can find all this information in our research publications. We are publishing papers annually together with our industry partners. And yeah, here you can see the links for the latest paper, for project website, Google Play, and desktop version of the application. So thank you for your attention. I don't know if we have time for any questions.
We have time for one question. If you want to go to the mics, one here and one there. In the meantime, I have a question. It seems that the maturity of mobile deep learning libraries is a big blocker in this case, the lack of maturity, I would say. How can you imagine that we overcome this difficulty?
There is a clear evolution in terms of the number of ops, in terms of performance of mobile machine learning libraries. So in case of TensorFlow, there is actually a huge group of developers that is working on this library. So I can expect that in a couple of years it will get much more operators, will get support for much more operators, and there won't be much difference between a standard and mobile TensorFlow library. And you also saw that PyTorch started to develop their solution, and in case of PyTorch, if they add support for Android and NNAPI, support for Delegates, or any other support for running AI models with acceleration, probably all problems will also be solved.
Very quickly, go ahead.
Are all of these chips in iPhones, etc., really public? Like is the Edge TPU or what's accelerating within Apple? Was this also tested, or are some of these just specific to some of the vendors like Apple and they're not included in the comparison?
Yes, Apple was not included into comparison because there is no standard way for accessing, for accelerating neural networks on Apple devices. So Apple doesn't have an NNAPI, it's quite clear. And Apple cannot run TensorFlow Lite models with acceleration. I mean, you can technically use just a GPU delegate, but this delegate was also developed by Google, and it doesn't reveal the full power of their chipset. So in case of Apple, you need to use external, their own SDK, their own CoreML system. So you basically, there is no straightforward way how to compare the performance of iPhones and Android devices. So in case of Android devices, everything was just identical in all cases. So all devices were tested under identical conditions. They were running absolutely the same models with absolutely the same library. In case of Apple, they can, for instance, sacrifice an accuracy and they will get better performance, better runtime. They can modify some ops and say, well, you won't be getting the results that you're expecting to get. So, and in this case, there is no control over inference on Apple devices. So it's basically just another world.
Thank you, Andrey. Thank you. If you have more questions, don't hesitate to ping Andrey at the break just after. Thanks.